Welcome to this online course on continuum mechanics and transfer phenomena. This lecture is about the introduction to the course. This course introduction I split into 3 parts. The first part is on measurement and prediction. The second part is on overview of transfer phenomena, and in the third part we look at the scope of the course. And this is the outline of the first part on measurement and prediction. First we discuss two different ways of analyzing a process, namely experimental method and the theoretical method. The theoretical method, two different approaches are possible. One is the thermodynamic approach, which we discuss next, and then the transfer phenomena approach, which we discussed following that. So, let us start with a simple experiment. What I have here is a small tank. It has 2 inlets and then an outlet. Water flows in through the 2 inlets and then flows out through the outlet, and we maintain a steady state condition, which means the liquid level in the tank is constant. So, just 2 flows coming in and then a flow leaving the tank. Okay. Now, we measure the flow rate of both the inlet streams. The measurement values were 12 milliliter per second and 9.8 milliliter per second. Okay. So, we measure the volumetric flow rate of both the inlet streams. Okay. Now, coming to the outlet stream, I also measure the volumetric flow rate of outlet stream, which turns out to be 22.1 milliliter per second. Okay. So, I measure the volumetric flow rate outlet stream. The keyword is measure because I am measuring both the inlet streams and the volumetric flow rate of the outlet stream as well. So, we have done an experiment where we have measured all the 3 flow rates. Okay. So, alternatively, let us look at the theoretical approach, wherein I once again measure the inlet flow rates of both the streams, which of course 12 and 9.8, but now I wish to predict the outlet flow rate instead of measuring the outlet flow rate. Okay. So, in the first case we measured it, in the second case we want to predict it. Okay. So, now to predict it we will use a simple mass balance, and for this simple tank with 2 inlets and 1 outlet, the mass balance is very simple, just says that mass flow rate leaving through the outlet stream is equal to the sum of mass flow rates entering through the 2 inlet streams. So, if you want to use some express in terms of algebraic equation, it says m dot out, m dot represents the rate of mass flow rate and out represents that is leaving, is equal to m dot in 1 and m dot in 2, okay, which are the mass flow rates of the inlet these 2 streams. Okay. Now, what we have in this particular case is just water entering and then leaving. So, the densities are same or almost same. So, just becomes a balance of volumetric flow rates. So, in this case it just becomes volumetric flow rate leaving is equal to sum of volumetric flow rates entering. So, q dot out is equal to q dot in 1 plus q dot in 2. Okay. Because density cancels out, just becomes a balance of volumetric flow rate. Now, here I use the measured values of the volumetric flow rates of both the inlet streams and then substitute in this equation and then get the volumetric flow rate of the outlet stream. So, I substitute 12.0 and 9.8 and predict the value of volumetric flow rate of outlet stream as 21.8 milliliters per second. Okay. So, second case we have measured or made only 2 measurements and predicted the value of the outlet flow rate using a mass balance, in which this case becomes a volumetric balance. So, to summarize what we have done, we have predicted flow rate of 21.8 milliliters per second, which compares with the measured flow rate of 22.1 is a small difference about 1.4%, which can be attributed to several reasons, measurement error, variation in flow rate and so on. Okay. So, to put formally what we have done, we have experimentally measured outlet flow rate and predicted using mass balance, that is what we have done in the last slide. Okay. Now, and then of course, we compare this predicted flow rate with the measured flow rate. These two things are what we have done in the last slide. Okay. Now, this mass balance comes from the principle of conservation of mass, which we call as theory. Okay. And this mass conservation equation we call as a mathematical model for this simple process. This process is extremely simple. You have just two inlets and one outlet. It is operating under steady state condition. No second component is present. All temperatures are the same. The densities also happen to be same. So, very simple process. And for this case, the mass conservation equation or the mass balance we wrote is called the mathematical model for this process. Okay. And this, why is it a model? This model mathematically mimics the process or represents the process. Experimentally, we had two flow rates, they got summed up and result in outlet flow rate. Similarly, the equation also sums up both the inlet flow rates and gives you an outlet flow rate. That is why this model mathematically mimics the process, represents the process. Okay. Now, other way of telling this is we have simulated the process using a mathematical model, in short model. The way in which we use model in this course represents a mathematical model. Okay. Otherwise, to begin with we say mathematical model, but moment we say model represents the term mathematical model, in short we say as model. Okay. And so, we have simulated the process using the mathematical model. So, what is the whole objective? Objective is to use this model to predict the measured value, not just predict, we want to be as close as possible. Okay. So, the summary of these two slides is that we want to use a model and then predict the measured value, in this case the outlet flow rate, and also as close as possible. Okay. Now, just look at some terminology which I have used. Process, in this case the tank with the inflows and outflows, that is our process. Okay. And the measurements, two inlet flow rates and the outlet flow rate also. If you want to experimentally analyze this process, you measure the outlet flow rate. Suppose you want to check your model, you once again measure the outlet flow rate. In both the cases, you need to measure the outlet flow rate. Okay. And then the theory, in this case the conservation of mass, and then the model is the mass balance equation which I used. Okay. And then simulation is the solving of the model, and the prediction is the result of the simulation, in this case it is the outlet flow rate. So, it is process, the tank, the measurements, the three measurements which are taken, 2 or 3 measurements which are taken, theory, the conservation of mass, the model is a mass balance equation, and simulation the solution of the model, solving the model, prediction is the final result, that is the result of simulation. Okay. Okay. So, what is the need for theory, model, simulation, why is it required? Okay. First thing is to understand the physical principles behind the process. In this case, we understand that a simple mass balance takes place. So, helps us to understand the physical principles behind the process. Okay. Second, experiments need not be conducted for a different values of input variables. In the example which you have seen, so the flow rates were some set value. Suppose you change the inlet flow rates and then you measure the outlet flow rate. You need not do this experiment several times. If you have a model for this process, it is enough if you know the inlet flow rates, you can predict the outlet flow rate. So, experiments need not be conducted for all values of input variables. Okay. Which means you can analyze the effect of different operating conditions. As I explained you, even for different values of input flow rates, you can use the model and predict the outlet flow rate. Okay. You can also determine the size of equipments in a chemical engineering plant, which you call as design. Usually when you find size, the terminology becomes a design. Okay. And for example, if you have a heat exchanger in a chemical engineering plant, you find the area of the heat exchanger using model, it becomes a design. Okay. And because advantage of model and theory is that based on few theoretical principles, you can simulate a wide range of processes. The theoretical principles governing different processes are same, a small set. So, if we understand them, we can simulate a wide range of processes. Okay, that is the advantage of theory and model. Okay. Okay. So, now what we will do is extend what we have discussed for a simple process, namely the tank, to an entire flow sheet. Okay. What we are seeing here is flow sheet for the manufacture of ammonia. Okay. We have nitrogen, hydrogen entering, and it may have some impurities as well, and based on thermodynamics, okay, the nitrogen hydrogen reaction giving ammonia has to be conducted at high pressure, and for increasing the rate of reaction we need to conduct at high temperature. So, it is a high temperature high pressure reaction. So, we need to compress the inlet gas to the high pressure of let us say 200 atmosphere. So, we need a compressor which compresses from let us say atmospheric pressure to a high pressure of 200 atmosphere, and that stream enters a God reactor which removes some impurities which will impair the activity of the catalyst. Okay. It is a catalytic reaction and iron is used as a catalyst, and so we remove those impurities in the God reactor. Okay. Enters the main reactor, it is a catalytic reactor using iron as a catalyst, conditions as I mentioned of 500 degrees and 200 atmosphere. This reversible reaction between nitrogen hydrogen giving ammonia takes place. Okay. And it should be noted the conversion is usually very low, order of just 20% per pass. Okay. And the stream leaving the reactor has ammonia, unreacted nitrogen hydrogen and some impurity as well, let us say argon. Okay. And now we need to separate ammonia from this stream. We do the first condensation using cooling water, and where part of the ammonia condenses out as a liquid. So, you send it to a gas liquid separator, simple gas liquid separator where separation takes place by gravity, and so liquid ammonia comes out, that is also part of the product stream, and the remaining stream goes to the refrigerator. Based on the high pressure of 200 atmosphere, you need a temperature of about minus 15 degrees centigrade, so that the ammonia going in this stream is as minimum as possible. If you maintain at a higher temperature, let us say more than minus 15 degrees centigrade, then there will be enough amount of ammonia in this stream which you do not want to happen. You want most of the ammonia to be in this stream. So, you maintain a very low temperature of minus 15 degrees centigrade, that is why you require a refrigeration. Okay. Okay, so, now ammonia condenses out from the refrigeration unit also, and these two ammonia streams are mixed, and that is our product ammonia. Okay. Now, the recycle stream has argon in it, so which we do not want to accumulate. So, we have a purge which avoids accumulation of argon in this cycle, and then of course unreacted nitrogen hydrogen is recycled back to the main reactor. And because there is some loss of pressure during the process, we have a small compressor which makes up for this difference in pressure. So, whatever let us say 200 bar comes down, let us say 190 bar, it adds up to 10 bar extra and brings it back 200 atmosphere. Okay. So, let us say we want to set up this ammonia plant and we want to design this plant, we want to simulate this plant. Okay. Now, how do we go about that? Okay. Now, as I say, simulate is equivalent to prediction of variables. Now, what are the variables which we like to predict in this particular flow sheet? Okay. First, for a given flow rate of the feed and operating conditions, let us say we are given the feed and the operating conditions are given, what are the variables we like to predict? Okay. First, we have the compressor unit. So, we like to predict the power required for compression of the feed gas. We are going from a atmospheric pressure, let us say, to a very high pressure. So, a lot of power is required. What is the power required in the compressor? Okay. Now, we have the main reactor. What is the conversion of hydrogen in this reactor? We like to know that as well. Okay. And that determines the quantity of ammonia produced. And we have separation of ammonia from the unreacted reactants. Some separation takes place in the condenser, some separation takes place in the refrigerator. Those are, we also like to find out what is the composition of the stream leaving the condenser, leaving the refrigerator. And of course, finally, we also require the flow rate of cooling water. We have cooling water here, cooling water entering and leaving. We also send in ammonia refrigerant here. So, we like to find out what is the flow rate of cooling water, what is the flow rate of refrigerant required in these two units. Okay. Of course, we also wish to find out what is the production rate of ammonia for different operating conditions. So, we like to predict the power for the compressor, the conversion in the reactor, and then the composition of vapor leaving, and the flow rate of the coolants required, and the production rate of ammonia. Okay. Now, what other variables we like to predict? Okay. Now, these variables I am going to discuss fall in the category of something to do with size, area, etc. of the equipments. Okay. So, we want to predict, or we want to know the size of the reactor. What do you mean by size of the reactor? As I said some time back, it's we have used a catalytic reactor. We use a multi-tubular catalytic reactor shown here. So, when I say size, I mean mass of catalyst required. So, which is equivalent to finding out what is the length of the tubes required, number of tubes required. So, mass of catalyst required can be expressed in terms of length and number of tubes, that gives the size of the reactor. Okay. Now, we also want to know the size of the condenser and the refrigerator, which are heat exchangers. So, what do I mean by size of heat exchanger? I mean the length of the tubes, let us say a multi-tubular heat exchanger, shell and tube heat exchanger. Then I need to know the length of the tubes and also the number of tubes in the heat exchanger. Okay. And also like to know the size of the liquid vapor separator. What I mean by size here, what is the height of the separator and what is the diameter of the separator. Okay. So, as I told you, these process variables, these are also process variables which I like to predict, but these fall into the category of sizes of these equipment, size of reactor, condenser or liquid vapor separator. Okay. You will shortly know why I distinguish these two kind of process variables. Okay. Okay. Now, having taken a process calculation course, what are the variables which we can predict among this list? Okay. Okay. First, once again, of course, for given flow rate of feed and operating conditions, we can calculate the power required for compression of the feed gas, and of course, we can find out the process calculation course, a mini thermodynamics course. Okay. So, based on principles of thermodynamics, you can calculate the minimum power required for compression. Okay. Now, we can find out the conversion of hydrogen in the reactor, and we can find out what is the maximum possible conversion, let us say using a law of mass action. You can find out the maximum conversion of hydrogen in the reactor. Okay. Now, we can also find out the composition of vapor leaving the condenser, leaving the refrigerator, and that we assume equilibrium and find out the equilibrium value of composition of the vapor leaving the condenser and refrigerator. Okay. Now, we can also do a simple energy balance around the condenser and then around the refrigerator and find out what is the flow rate of cooling water, what is the flow rate of ammonia refrigerant required. Of course, doing a mass balance and energy balance for the entire plant, we can find out what is the production rate of ammonia. So, based on the knowledge gained from a process calculation course, it's a simple thermodynamics course, you can solve for different variables in the plant, namely power required for compression, conversion of hydrogen in the reactor, composition of vapor leaving the condenser and refrigerator, cooling water required in them, and the production rate of ammonia. Okay. Now, what are the variables which we cannot predict based on a process calculation course? Whatever variables we classified as size, falls in the category of size, they cannot be predicted using a process calculation course knowledge. For example, the size of reactor cannot be predicted, the size of the condenser, refrigerator, heat exchanger, that cannot be predicted, and then of course size of the liquid vapor separator can also not be predicted. So, all other variables like power etc. could be predicted, but whatever has to do with size cannot be predicted using the knowledge gained from a process calculation course. Now, what are the assumptions made in a process calculation course? Okay. Now, for calculating the power required for compression of the feed gas, we said we will get the minimum power required. This power required is calculated from enthalpy change. Okay. So, in a process calculation course, we assume that the gas is ideal, and hence we assume the enthalpy to depend on the temperature only. Okay. So, based on the assumption that it is an ideal gas and the enthalpy depends on temperature only, we will find out what is the power required. Okay. Now, regarding the composition of vapor leaving the condenser refrigerator, we will assume vapor liquid equilibrium, okay, and we will use Raoult's law or Henry's law depending on the case, and then we will also assume it is a mixture of ideal gases, we will also assume it is a ideal mixture of liquids. Okay. So, based on all these assumptions, mixture of ideal gases, ideal mixture of liquids, we will assume the vapor liquid under equilibrium and find out the composition of vapor leaving the condenser refrigerator. Okay. Okay, now coming to the conversion of hydrogen in the reactor, for reaction equilibrium we assume the law of mass action, okay. We use the law of mass action, and then we assume the to be a mixture of ideal gases and find out the conversion of hydrogen in the reactor. Of course, we get the minimum power required, the equilibrium value of composition and the maximum conversion in the reactor. Okay. Now, as I have been telling, the process calculation course is a mini thermodynamics course. So, now suppose now if you take a full fledged chemical engineering thermodynamics course, what are the improvements possible in these prediction values? Okay. So, let us start with the power required for compression of the feed gas. For enthalpy change calculation, in the earlier case we assume the gas to behave ideal, but now we will assume the gas to behave as a real gas. Okay. What is the implication? The enthalpy which was assumed to depend only on temperature will take the dependency of enthalpy both on temperature and pressure, which makes it a better value. Okay. Now, coming to the composition of vapor leaving the condenser refrigerator, for vapor equilibrium we assumed all ideal conditions, okay, Raoult's law, Henry's law, etc. Now, we will assume a modified Raoult's law, modified Henry's law. How do we modify? In the earlier case we took mixture of ideal gases, but now we will say it is a non-ideal mixture of real gases. So, we take into account the non-ideality in the gas phase. Also, for the liquid phase we assumed ideal mixture of liquids, but now we will take it as non-ideal mixture of liquids. So, we take into account the non-ideality both in the vapor phase and the liquid phase and make better prediction of the equilibrium value. Okay. When I say better prediction, as we have seen in the beginning slide, better prediction means closer to reality. Okay. Okay, now coming to the conversion of hydrogen in the reactor, we assume of course reaction equilibrium, we assume law of mass action, but we will use a more general expression based on a general equilibrium relationship. Okay. Now, we also assume mixture of ideal gases, here again we will assume non-ideal mixture of real gases. So, here again we take into account the non-ideal behavior of the gases. So, the improvements in the chemical and thermodynamics course is that we take into account the non-ideality and the predicted values are going to be closer to experimental values, okay, because we take into account non-ideality. So, that gives us the scope of a thermodynamics course. Now, in thermodynamics we talk about process going from one equilibrium state to another equilibrium state, and thermodynamics always gives us the limits of performance, as we have seen. For example, it gives the minimum work required in the compressor. Equilibrium composition, which is the composition which you would attain if they were in contact for a very long time, okay, which is the maximum composition, okay, and the maximum conversion possible in the reactor. So, it talks about minimum, maximum, equilibrium, etc. Okay. Now, what is outside the scope of thermodynamics is the rate at which the process happens. How fast it happens, how slow it happens is not under the scope of thermodynamics. Okay. So, it talks about limits of performance, talks about process going from one state to another, does not talk about how fast the process happens. Okay. So, that brings in the scope of transfer phenomena, because we need to take into account the rate at which the process happens, so that you can find out the size of equipments. Okay. Size of equipments is not under the scope of thermodynamics, we need to predict them, and that is where scope of transfer phenomena comes in. Okay. So, to predict actual performance and size of equipment, rate of the processes has to be considered. Okay. That is the central theme behind the scope of transfer phenomena. Okay. So, transfer phenomena considers or includes the rate at which processes takes place. Okay. And what does it transfer phenomena includes? Includes three closely related topics, namely fluid mechanics or momentum transfer, okay, which deals with transport of momentum, okay, and then heat transfer, which deals with transport of energy, and mass transfer, which deals with transport of mass. When I say mass, I mean mass of species. Okay. So, subject of transfer phenomena is required to take into account the rate of processes, rate which process happens, how fast, how slow, and why is it required? To predict the actual performance. Thermodynamics limits itself to the limits of performance, but we like to predict the actual performance, find out the size of equipment. So, we need to consider rate, and transfer phenomena does that. And the subject of transfer phenomena includes three closely related topics: fluid mechanics or momentum transfer, heat transfer, mass transfer, deal with transport of momentum, transport of energy, transport of mass of species.